Right, so good afternoon, everyone, and welcome to the USEV Microcontrollers Workshop today. To start with, this session is being recorded, and then it will be uploaded to the USEV YouTube channel later on. This will just be an audio recording plus the screen sharing that I'm doing, so your faces won't be visible if you don't want that. And of course, please ask questions anytime during the presentation, and so I would just speak up or post them in the chat, and one of us will get those answered. So to start with, I just want to go over the agenda for this afternoon. Firstly, I'm going to give a short presentation with some sort of background into the microcontrollers and Arduino programming, to hopefully give you all a good first leg to stand on. After that, I'm going to do a bit of a coding demo with Arduino. So I'm going to bring up the Arduino IDE and work through an example, and then just hopefully by that you can get a bit of an understanding as to some of the common functions and design techniques for microcontroller programming. These two sections are going to be fairly short, so I hope that we'll be able to get those completed by about past. And then following that, we are going to go into a tutorial. So we've selected a bunch of tutorial examples that we found online for a range of different levels, from beginner, intermediate, and advanced. And so hopefully there should be something for everyone to look at. And as I said, of course, like we're going to be we're more than happy to answer any questions, both throughout the presentation and the coding demo, and then also when we're in the tutorial, you'll be able to ask questions, and myself, Ross, and James will be on standby to answer any questions or help you if you get any debugging of code that you need to do. So let's start with, what is a microcontroller? So to put it simply, a microcontroller is a small and low power processor, also very low cost, which integrates your central processing unit, which is your CPU, which is actually doing all of your computation, plus some memory for storing data in your program, and also your peripherals. So the peripherals are for interfacing with the outside world, essentially. And it takes all of those and puts it into a single package, which is really easy to work with, and also very small, so you can put it in a lot of designs. So these features that it has make it really well suited to fairly basic tasks, things like interfacing with sensors, controlling peripherals, things like motors, etc. That's all very common, which obviously means that they have a large amount of uses in everyday objects, and of course in USEV. The programs that they run are fairly basic. They're written in what we refer to as a low-level software language, something like C or C++. Arduino, the programming side of Arduino, is derived from C++. But don't worry if you've never done any C or C++ programming before. That's absolutely fine. You can easily pick it up. But that being said, like, these days there are microcontrollers that can get a lot more advanced than just this, and there are suited to much more complex tasks than just controlling things like sensors and motors. NXP, for instance, have a microcontroller coming out fairly soon, which can operate at over 1 gigahertz. And at that sort of speed, you're looking at performance that is comparable to some of the basic Linux-capable processors. And people are also developing methods for programming them in different languages. So things like Python is becoming quite popular these days for programming microcontrollers, and that's obviously a much higher level language than something like C and C++. So that's sort of the basic side of the way. Let's now go in and have a look at what's actually inside a microcontroller. So this rather low resolution diagram is quite a nice representation of a simple microcontroller. This is not the same as a lot of Arduino products or even the STM32 microcontrollers that we're using in USEV, but it's fairly scaled down, and has sort of just the bare minimum of stuff, which makes it nice to go over now. So at the heart of the microcontroller, you've got your actual processor core, as I mentioned. So in this case, this is called an STM8. That's the name of the core. And you can see that it's running at 24 megahertz. So this is the clock speed, and then a higher clock speed means that you can perform more operations every second. And that is where your program is actually executed, that you write. So you've got your processor, and then that needs to be able to do a lot more than just what it is generally capable of. So there are a bunch of other blocks that you can see here that make up the full microcontroller system. And the processor core itself is able to control each of those and get it to do whatever it is best at doing. So let's have a look at a few of those now. So in the red, you can see that you've got some memory. So there are generally two types of memory. There is flash memory, which is, as you might know, it is non-volatile storage, which means that it doesn't require power for you to keep for it to hold data. So that's where you're going to be storing things like your program before you actually start executing it. Large amounts of data, if you're collecting that from a sensor or something, you can often put that into flash memory. And basically anything that you want to save once the microcontroller has been turned off. Then you've got RAM, which, as many of you will know as well, is a volatile storage, which means you need to apply power to it for it to keep the data stored in it. And the RAM is where your program is executed from. So when you turn it on, your program moves from flash into RAM, and then from there, the microcontroller core can read off what it's supposed to do. Moving away from the memory now, we can have a look at some of the other peripherals that are in the design. So peripherals are what the microcontroller uses to talk to the outside world. First of all, down at the bottom left, we have IOs. So these are our digital inputs and outputs. That's fairly self-explanatory. You can either write a logic high or a logic low to any of your pins. Then over just below the memory in the purple, you have what are called ADCs. So these are analog to digital converters. They take in, they measure an analog voltage that's on one of the pins, and then they convert that into a number which can then be read and processed by the CPU. Over on the right-hand side in the blue, you will see a lot of timers. So we're not going to focus too much on timers currently, because Arduino kind of hides the timers from the user, and they're a bit more advanced to be using them. However, as the name suggests, they are going to be used for controlling precisely timed events. So if you need a certain signal to trigger every 27 microseconds, for instance, you'd be using a timer for that, and that's going to be able to get very precise timing. And above that, and also I guess below the ADC, are some green blocks, and these are your communications controllers. So in the world of embedded systems, there are a number of communication standards, and these are basic communication protocols that you can use for sending data between one or two or more devices. And to make those work really smoothly on microcontrollers, you will generally have an integrated controller. So as you can see here, we've got things like UART, I2C, SPI, CAN bus. These might be a bit unfamiliar to you, but as you go through like working, if you get a sensor which you need to interface with I2C, which is actually what we're going to be doing in the coding demo later, you can go and easily interface with that through this I2C controller that's already on your microcontroller. So we're now going to jump in and have a bit of a look at Arduino itself. So Arduino, there are kind of two parts to Arduino. There's the hardware, where the Arduino Foundation produce hardware that you can buy, We're not going to be using that in USEV. Some of you guys might already have Arduino hardware that you've used before. But we're going to be focusing more on the software side of things. So Arduino have produced what's kind of referred to as a framework, which is used for easily programming your microcontrollers. So normally in a microcontroller, you have to deal with setting and resetting registers and setting bits high and low, which can make things quite complex to actually work on. Whereas in Arduino, you have a bunch of high-level functions that you can call, and it's a much more user-friendly and intuitive way of working with hardware at a low level. The programming language itself is based on C++. So if you've done any work in C++, you will be very comfortable. But if you've not touched C++ before, or even C, don't worry at all. You're not going to be at a disadvantage. I personally learned Arduino before I even knew what C or C++ was. So you won't have any problems there, and there are a lot of tutorials online. And so ultimately, in addition to this sort of slightly adapted language, Arduino provides a bunch of functions and classes which are designed to make programming simpler. So we're going to have a look at some of those on the next slide. So this is a very basic piece of Arduino code. Doesn't really have much of a purpose apart from to essentially flash an LED, but it's a good example of a lot of the different things that you can do in Arduino coding. So I'm just going to start by going through some of this now. If you've got any questions as I'm going through it, if I've not explained something as well as you think I should have, by all means, just interrupt, and I can go over that again. So first up at the top here, what we have is a define statement. This is what's called a preprocessor constant. And essentially how this is working is every time the code sees the word analog_threshold in your code, it will replace it with the number 128. So you can see further down in this if statement, you have analog_threshold. That would be replaced with the number 128. So that's a constant, but then that means that you cannot actually write any value to it. It's a read-only value. However, in a lot of cases, you're going to want to be able to both read and write to a piece of memory. And in that case, you want to use a variable. So below that, you can see we've defined two variables, one called analog_in and one called button_in. And these are going to be used for setting and reading from different peripherals eventually. Like sort of C and C++, Arduino is what we refer to as a typed language. So many of you will have used Python before. That is pretty much an untyped language. So by that, I mean data types don't really matter. In Python, you can just declare a variable and set it to a number without even thinking about it. Whereas in C and C++, and therefore in Arduino, we need to kind of think about how much memory is that going to use up. So in this case, before the name of the variable, we are defining it as being an int. So this is the data type, and int in this case stands for integer, which is one of the more common data types that you can use. And this is a 32-bit value. And that works quite nicely in a lot of microcontrollers because generally microcontrollers these days are 32-bit. So 32-bit numbers works really well in those. Then we go to the first of our sort of Arduino specific functions. So in this case, we've got one called setup. And setup is a function that you need to have in your Arduino code. And as the name suggests, it is responsible for setting things up. It runs once when you power the device on, and it also runs every time you reset the device. And in this case, what we're doing is we are calling two functions called pin mode. And the pin mode function is used for setting up your digital inputs and outputs. So in this case, what we're doing is we are saying that digital pin 1 is an input and digital pin 13 is an output. And we need to specify inputs and outputs because of essentially the way that your GPIO controller works internally in the microcontroller. After that, we've got the second of our Arduino specific functions, and that is loop. So as the name suggests, this will run indefinitely until either you disconnect power from your microcontroller or until you reset the device. So when we get into here, this is generally where we do the actual processing of data. So your setup function sets everything up, and then your loop function is where you're actually dealing with getting data, processing data, outputting data, etc. So the first thing we do here, as you can see, is we are taking these two variables that you will remember we defined earlier on, called analog in and button in, and setting those to we're using two unique Arduino functions, one called analog read and one called digital read, to read a value from a pin. So in the first example, we are reading a value from analog pin A0, and we're storing that value in the variable analog in. And in the second example, we are reading a value from digital pin 1 and storing that in the variable button in. The next thing that we're doing is we're actually having a look at that data and saying, okay, right, depending on that, depending on the values of those pieces of data, we're going to do something slightly different. So you've most likely come across if statements before, if you've done any sort of programming, and fairly simple. We are evaluating what is inside the brackets, and if this expression evaluates to true, we're going to execute what is inside the if statement. So in this case, what we're doing is we're saying, okay, if the analog input that we've just read from pin A0 is greater than our analog threshold, which, if you remember, that was 128, and our button in is not equal to 0, so our button is pressed, essentially, then if that is true, we are going to do a digital write to pin 13. So in this case, that is writing either a 1 or a 0, a logic high or a logic low. And in this case, it's as you can see, it's a logic high, but we write to pin 13. However, if that condition that we set up in the if statement is not met, we need to go down into our else statement. And here, what we're going to do is we're first going to call a delay function, which is, again, another Arduino specific function. And we're going to delay the CPU for 1,000 milliseconds. After that 1,000 milliseconds is up, we're going to do our digital write function, except this time, instead of a logic high, we're going to be writing a logic low. And then after that, we just go right back up to the beginning of our loop function and get our analog read and digital read values once more. So does anyone have any questions about that currently? Right, I see. So Joshua, do you need to set up pin A0 or is it only for digital pins? No, so on the analog pins, because these are only analog inputs, it is automatically inferred that you're going to be working with the input. I believe in some devices you will be able to have, I'm not sure how Arduino deals with this, but in some devices you might have a pin which is shared between an analog to digital converter and a digital to analog converter. I'm not quite sure how that would work, but I've not really come across any Arduinos that have that feature. But in general, if you're doing an analog read, you won't need to set the direction of the input because it's automatically inferred. So what's the purpose of the 1,000 millisecond delay? There isn't really one in this case. That I just decided that to include that to show you that you can do delays. In general, you should try and avoid delays in microcontrollers, especially using this form of delay, because this delay is essentially implemented as sending a bunch of what are called no-ops or no-operation instructions to the CPU. And so the CPU is continuously doing stuff throughout that delay, and it's using power, but you're not actually doing anything useful. But in some cases, it's useful to have a short delay. So if you've just set up something, and in some cases you need to, especially with things like analog components, you need to wait for maybe a few milliseconds for that analog component to sort of stabilize. And in that case, you can use a delay just to stop the CPU from proceeding with the code until that analog component has stabilized and is ready to move on. Any other questions before we move on? Okay, so we've thought about the Arduino code and essentially how we as programmers are writing it, but how does this actually translate into what the microcontroller does? So I don't expect you to fully understand all of this stuff, but it's useful to know. So once you've written your code, you pass it into a program called a compiler. And what the compiler does is it takes your code, whether that be Arduino or C or C++, and it converts it into a very low-level machine code, which we refer to as assembly. And the assembly code basically only contains labels and processor instructions. And this is simple enough that the processor can then go and read through this and execute exactly what is in that assembly code. So this is just a little example that I've made up. You by no means have to understand this, but I think it's nice to know that it's nice to be able to see how you've got a relationship between these two pieces of code. So you can see what we've got. We're working with the numbers 10 and 12 here, and these numbers also correspond to an instruction in your assembly code. We've got some adding happening over in our C code, and we've got an add instruction being called in the microcontroller, a multiply being done in the C code, and a multiply instruction happening in the microcontroller. And then your if and your else statements, they get a bit complicated with branches and jumps. So you don't really need to worry about that. Assembly code is sometimes used these days for very, very, very time and critical tasks. However, generally compilers these days are good enough that you can kind of just forget about doing assembly code and purely focus on doing C and C++, which is a lot friendlier. So this is more for the guys that are in the electronics teams. This is the microcontroller that we're going to be working with. It's called an STM32 F302R8 from a company called ST Microelectronics. The microcontroller itself is a bit of a beast. It's got quite a lot of performance, more than we would probably need in what we're doing. It's got an ARM Cortex M4, so that's the actual processor that it's got, running at 72 megahertz. So that is about 3 times the speed of the smaller microcontroller that we looked at a bit earlier on in the block diagram. And it also has a lot more features than that. So it's got what's called a floating point unit, which allows it to work with very large and very large and very small numbers. It's got more flash and RAM. It's got an analog to digital converter, and then it's also got the opposite of that, a digital to analog converter. It's got 9 timers, a bunch of other communications interfaces, so I2C, UART, SPI, USB, CAN bus. I dare say that a lot of people in USEV will be working with at least one of those, and so that will be a useful thing for you to understand a little bit about. Interestingly, it's also got a few analog components. I'm not sure if we'll ever make use of these. It's got a few analog comparators and a few op amps. which you can kind of configure are sort of programmable inside the device. It's got 51 inputs and outputs. These are digital inputs and outputs. And the important thing to note about these pins is that they operate at 3.3 volts. So a lot of, due to sort of the design of silicon in the past, a lot of devices used to be operating on 5-volt logic. And even today, you do still get a lot of microcontrollers that run on 5 volts. And therefore, some peripherals that you might want to connect up to your microcontroller operate at 5 volts. So you need to make sure that everything is running at 3.3 volts, or you could damage either the microcontroller board or your peripheral. So finally, I just want to show this slide here. This is to kind of show that all of your peripherals and controllers that are inside the microcontroller, each of those is connected to maybe 1 or 2 input and output pins on the device. So when you're working with sort of your hardware and software integration, you need to be aware that you can't connect an analog to digital converter pin to any pin on your device. One analog to digital converter inside your device may only connect to 1 pin on your chip. And each of those, you might find in some cases that you have 2 devices that want to share the same pin, which obviously doesn't work. So it's good to be aware of that. And when you're doing hardware and software design, keep that in mind so that you don't run into any issues. So that is going to be the end of the presentation section. And now we're going to take a look at the coding demo.